Okay, good morning. We begin right now the session. Well, we already started the session today is Saturday, with Professor Clifford Johnson. He's coming from the University of Southern California, and he teaches deep brains, and the title of the course is exactly Introduction to Deep Brains.
So I don't know what kind of material you've seen so far in detail about string theory, but I think it probably might be useful, even if you've seen some of this, to repeat it a little bit. I'm going to talk some of the basic tools I need for what I'll need later. So this first lecture will mostly just be reminding you about the string theories, the 10-dimensional string theories. Okay, so you've probably seen some of this before, maybe using a different approach. One of the things you'll probably know from learning any topic, but especially something like string theory, is that it's useful to hear the same thing many times with many different approaches. So, because we're still learning so much about what the theory really is, so perhaps even if you've seen some of this before, it will be useful to hear it again. So, anytime you have questions, just stop me, raise your hand, or shout out, or something like that. So one of the things I'm going to do is maybe go a little bit quickly, because I think you will have seen some of the core concepts. But every now and again I will sort of slow down, because I'm going to emphasize some things that will be useful for me later on. So hopefully it will make sense. So first of all, let's start with reminding ourselves a little bit about what we could take to be one of the basic actions defining the string theory. So I'll define some of these things later on. Write it down first of all. Have you seen something like this before? Good, okay, that's encouraging. So what I've written here is an action, excuse me, so I've written down the two-dimensional action with, which has certain properties. So this you can think of as basically some sort of conformal field theory. Mu and nu I will use as space-time indices. Running from 0 to 9. So it's a 10-dimensional string action. There's a lot of work that has gone into showing that 10 dimensions is the number of dimensions that we wish to work in. I'm not going to review all of that. We simply don't have time. So I assume you've been convinced of that before. What I've also written here is implicitly I've made some choices. So I'll talk about that in a moment. These coordinates, z and z bar, sorry, my writing is a little, is it too small? It is too small. Okay, so you should let me know. This is a good size?
Yes. Yes.
Okay, but this is too small. Okay, good. I'll try and be consistent. I've been using chalk a lot this semester, and so my whatever this stuff is called, writing needs some practice. Right, so remember, a key thing here from this perspective is that we're doing this two-dimensional, we're in this two-dimensional world where we have these coordinates z and z bar. I'll remind you of their relationship to the coordinates that you probably saw before, which is tau and sigma. And from the point of view of that, these fields x and psi bar, or psi tilde, are simply a family of fields that live in two dimensions. And we know that there's another perspective, which is that this is also telling us about some supersymmetric string theory that lives in 10 dimensions, and this just happens to be the theory on its world sheet. So, that perspective, that moving back and forth between world sheet and space-time, or more generally world volume and space-time when we come to other objects, will be something we'll be doing a lot. So I'll just remind you of some of the things that we're doing here. I hope I can write on. This is also okay. Right. Generally, what we have in mind is that we have some parameterization of the string world sheet. Usually, whether it's an open or a closed string, you have in mind some picture where there's a string propagating in space-time. Sorry. There we go. And so there's some coordinates, and those coordinates are the x. 0, it's 1, it's 2, etc. Okay, and so that's the sort of picture. And then this action really is, if you like, a theory of maps, taking us from some idealized version of this world sheet. Into and those maps then look like that. Okay, so usually then we have the coordinates running from 0 to pi for an open string, or between 0 and 2 pi for a closed string. And then tau is a time coordinate like that. Once I get to here, I've made a number of choices. First of all, I've used what you probably used, a map from the plane to the cylinder. Not the cylinder. Excuse me a moment. Either this map or okay, so hopefully now I've got everything up I need. So I have Z. This map here is essentially telling us about how to go from this picture to either the upper half complex plane or the full complex plane. Is that something you've used before? Okay, good. All right, so I have, for example, in this situation, the string sort of having come in from infinitely far away at minus infinity, that gets mapped to the origin, and then the infinite out state is at the infinite boundary of the plane. Circulating in sigma then corresponds to doing circles in the coordinates here, and similarly over here for the equivalent string. Okay, so it's good to just have those pictures up. I'll be referring to some of the various of these objects as I go along, and so I'm glad to hear that you've seen some of this before. And at the end of the day, a lot of this comes from you've probably had these words: gauge fixing, the Polyakov action, picking a particular conformal gauge that gives this nice action. And so you could actually do that with a fully fermionized version of Polyakov and get this, or you could start with bosonic Polyakov and just get this piece and then go, I'm going to make it supersymmetric and just add these guys in as two-dimensional superpartners. And so, like I said, there are many, many different approaches to arrive at the starting point. I just wanted to have that up there. We're going to take this as our beginning. I'm going to remind you next of the mode expansions we use for this, solutions of the two-dimensional wave equations that come when you write down the equations of motion. So let me go straight to that then. Oh, and we'll also be using Euclidean signature for all the reasons I'm sure you've discussed already. Okay, so mode expansions. So, so generically, I'm going to be writing down x as a function of those two coordinates as a sum of pieces that look like this. I'm going to call one x left and the other x right. Okay, and x left and x right is essentially the same sort of structure, but you put bars and tildes on everything in the usual way. So a choice has been made. Right, there's one zero mode corresponding to the center of mass position of the string. Okay, when I add these two guys up to make this, it's just a thing I call x mu, and I just, because I can and it doesn't really matter, I've taken half of it to be in there and half of it to be in there. Okay, I could have made, you know, 2/3 and a third, or what have you. Doesn't matter. Okay, so this is so x mu, little x mu is the center of mass position. And then there's also the center of mass momentum, which I'm going to call p mu. And that's 1/2 alpha prime square rooted alpha 0. Oh, is the table in the way for some of you? I'm sorry. Right, so there's another zero mode, alpha 0, and that, and alpha tilde 0, and the sum of those with that normalization gives me the center of mass momentum. Now, when I'm doing momentum, when I'm doing a closed string, right, I have in mind the following picture. Let's draw that over. No, keep that. When I have in mind a closed string, right, what I should think of is that I have independent sectors. I have a left moving sector and a right moving sector, and they're completely independent of each other, right? Solving the two-dimensional wave equation, and I can write. I have either left or right moving sectors. I can, linear superposition says I can write the sum of any of those. So I have left and right moving sectors. Is that right or left? Okay, right moving. And so I have this, and I have this, and the tildes distinguish the oscillator modes for the right movers, and without tildes the left. When I come to the closed string, you can think of a closed string instead as made of standing waves, right? But it's essentially the same thing. I have left and right moving sectors, but they're reflected into each other, so they're not independent. Yeah. So that means, for example, that I'll get a relationship between alpha 0 and alpha 0 tilde. Okay. And so for the open string, once I make those two things equal, I'll get an additional factor of 2 here. It'll bring that root 2 upstairs. Okay, so that will be something we'll use later on when we come to open strings. We'll equate those two sectors, left and right moving. Okay, so what else should I tell you? Okay, so boundary conditions on the fermionic sector comes in two flavors. Because I have two different kinds of boundary conditions, depending upon whether I have periodicity or antiperiodicity. And so this is the Raymond and Neveu-Schwarz sectors. So two kinds of boundary conditions. Periodic or antiperiodic. Okay, that gives me what's called the Raymond sector, or the Neveu-Schwarz sector. Right, so I have side tilde. Mu 0, it's plus or minus. that. Okay, and so the mode expansion basically, it's very simple. I have mu z or z tilde and something like this, where I'm using psi with a mode to denote the modes for the psi, which is a little bit of a redundant notation, but hopefully won't be too confusing. So this r is either an integer or half integer. Depending on whether it's Riemann or short. So again, I imagine you've seen that because you were doing supersymmetric strings, and you probably talked about Riemann and short vectors a lot. We're going to need that as well. So the last thing I'd like to talk about then is the two-dimensional stress tensor. Both its bosonic and fermionic cousin, because we'll need to remember some of our mass shell conditions, which come from that sector. Are there any questions so far? Is this looking familiar? Is this okay? Done anything completely crazy yet? It's going to come. Okay, so good. So stress tensor. So I have two pieces. I have a bosonic piece. Well, I have four pieces. I have a bosonic piece, left moving, a bosonic piece, right moving, etc., etc. Let me just write down one copy of each and let you write down the other piece by simply going and putting bars on everything. Right, and then there's a fermionic part, which is like that. So again, I imagine you've spent a fair amount of time looking at this. You can construct mode expansions for these guys as well. And this gives you the famous Virasoro generators. Did you do this? Did you write down the extended Virasoro algebra? Talking about that. Okay, good, good. So, okay. Maybe I don't need to write it again then. Okay, let's write it. And then you end up with right, and there's a beautiful story which no doubt you spent a fair amount of time on discussing how to actually compute this algebra, compute that anomaly C, and what that all means. And sadly, time to go into that again. So it's a rather lovely story. But just want to get some of the key players upstairs on the board so that we can discuss. Right, so this is either number Schwartz or Ramon, -1 or 0. The important point here is that these L's and G's are built out of our various modes, right? You could actually define this and then actually by substitution of these modes actually compute what those are and then do that computation of the algebra to find out what the central charge and so on and so forth is. How am I going to do this? I'm going to remove this. The explicit decomposition of the L's looks like this. Writing it down, it allows us to talk about something very important. Right, there's a normal ordering that you must do. Very crucially, the L0 operator has an important contribution that I need to talk about. It's going to be really important for a lot of what we do, so we'll talk about it now. So did you talk about normal ordering and all of that stuff?
Sorry.
And then, yeah.
In the LASS, the relation of the reversal algebra is a commutator, not a...
Thank you, yeah. So what is A? A, right, is, well, there are many different ways of thinking about it, but one simple way is to think about it, is that it's some sort of zero-point energy, some sort of Casimir energy on the cylinder, some sort of zero-point energy that the various sectors have. And I want to just list what that is, because we're actually going to use this perhaps in more general ways than you've seen when we come to study various kinds of D-brane configurations. So I either have the Nova-Schwarz sector or the Ramon sector before, and that, oh, and I should have written here C. We've already seen that D is actually 10. So the zero-point energy here is, so you can think about it in different ways, but at the end of the day, here's some things that you studied elsewhere that I just have to tell you. Right? At the end of the day, you study the 10-dimensional theory. You build states. We'll talk a little bit about some of the states. You build states. You have some vacuum state. You perhaps start building states of interest by acting with the various oscillators and so on and so forth. And a number of things come about in addition to the fact that essentially d minus 2 d minus 2 out of the d possibilities tend to give us the physical states, right? And the choice usually is that mu equals 0 and 1 don't contribute. Right, that's a choice, but it's a choice that removes, if you recall, it removes the possibility of ghosts, space-time ghosts from the spectrum, objects with negative probability, and so on and so forth. Have you discussed this before? Right, and another way to think about it is that it's the required number of physical states that a 10-dimensional photon would have. So you know that that d minus 2 has its roots in some actual physics, if you understand from a space-time point of view as well. I'll remind you of some of that, but I need to say that right now, because what I'm going to do is I'm going to talk about the fact that each of these bosonic sectors produces a contribution to the 0-point energy, which is with the periodic boundary conditions on a boson minus 1/24, and there are 8 of them. So that's, I needed to remind you of that so you remember where the 8 comes from, because D is 10. Right, so I have 8 minus 1/24, and then the antiperiodic fermions each contribute with a minus 1/48, and when you add that all up, you get minus 1/2, and so that's what the A is for that case. And in the Raman sector, same contribution periodically, from the X's, periodic from the size, giving you 0. And so in that case, A is 0. Thank you, 24. Okay, so you probably did this before. You may have also been given this. We're going to use this, so keep a note of this. In general, I'm going to write down, I have something that I can always write as a half h bar omega as my moding, so as my 0-point energy, h bar is 1, so just half omega. It's either that for a boson, or minus 1/2 omega for a fermion. And then I can give you a slightly more general formula, which we're going to use later on, I hope, if we get there. If the modes are integer, I use theta equals 0. If the modes are half integer, it's theta equals 1/2. Okay. The reason I write that is because I will have situations where I have bosons that are also antiperiodic, and I'll need to compute the 0-point energy. So right now, you've maybe just seen this calculation where I always have periodic bosons and then either antiperiodic or periodic fermions. We're going to be going more general than that, so this will help us. So keep a note of that formula. Okay. So, so I already talked a little bit about this. D minus 2 having something to do with coming from making sure we're doing sensible physics, right? That comes from many different perspectives. One of them is that you're simply building states and then making sure that they satisfy what's called the physical state conditions. And let me remind you a little bit of that, because it's going to bring out some of the prototype things that we need to finish the construction. How long is the first lecture? Is it the lectures are 90 minutes? Okay, yeah, right. Okay, so a physical state condition, so you may have talked about this, I'm sure you have. Right, at the end of the day, the L's and the G's are generators of symmetries of the theory, and state should be annihilated by those generators in order to preserve the symmetry. So I have something, if I have a physical state, I should have something like this. And then you can just construct a state and make sure that it's annihilated by all these things, and it'll give conditions on the properties of that state. An example, a very important example, comes from L0. It's sort of the prototype for a lot of what goes on. So let's talk a little bit about L0, and that's important because it's in the L0 sector. It's in L0. It's precisely in that sector that this comes from, plays a role. Okay, so L0, which is essentially the two-dimensional Hamiltonian. So I just stick, I just stick n equals 0 in here, so let me not write that out again. And I can write that. In different ways. So I have a sum from minus infinity to infinity here. I actually end up typically writing this as twice with the normal ordering and prescription in place. I can write that as twice. So I have alpha minus n alpha n, and so I can write the sum of the negative integers and the sum of the positive integers as equal to each other, and then just put a factor of 2, killing the half, giving me n equals 1 to infinity, alpha minus n, dot alpha n plus r okay, but there's one creature that doesn't fit in that sum, and that's the n equals 0 sector. So let's write that out, and that is 1/2 alpha 0 squared, right? And but if I remember now that alpha 0 mu is 2 alpha primed to the half p mu, right, from before, then I can write this as, I can write this term as, oh, excuse me, that's plus a. I can write this term as alpha primed p mu. Oh, thank you. Or for shorthand, I could have just put brackets and some of the as well. But the point is that p mu is minus m squared, right? It's in the space-time sense. And so I can write this as minus alpha prime m squared. Right? M in space-time. And so L0, annihilating something, you can see then is also a mass shell condition, which is this. Okay, let me rewrite that. So m squared. So L0 equals 0. Sorry, L0 acting on something equals 0. Or really L0 plus L0 bar in the case of full closed string. Right, that ends up being mass shell condition that looks like this. That is either minus a half or 0, depending upon whether I'm in the Schwartz. Okay, so so that's important, and it's important because it allows us, for example, to start looking explicitly at some of the low-lying states, which maybe you've done in some of the other courses. Let me just remind you of a couple of the basic ones, because we're going to use that to build the whole massless spectrum shortly. So in the open string sector, was there a question? Yeah.
How is this L0 bar?
Right, so I have this, and I can write this guy, right? And then I have tildes on everything, and I call that L0 bar. Yeah. Similarly, switching. Yeah. So there's two commuting copies of the algebra, and so I guess we should have said also, I guess here I should have said also L0 bar, sorry, LM bar, also LM, I guess tilde or bar, I guess. Right, and then I write down another identical copy of this algebra with bars on everything. And then, but I also write down an algebra where everything commutes to 0. Anything with a bar with anything without a bar gives me 0, because they're commuting. They're completely independent sectors.
Can you repeat why the physical states are annihilated by the Virasoro operator?
Because those are symmetries.
Ah.
And so that's what I mean. That's how I impose symmetries at the operator level, right? So remember, essentially the appearance of the conformal generators is just a remnant of the fact that I'm doing a conformal field theory, and so it has conformal invariance, which is spoiled by the anomaly. But once we end up in 10 dimensions and blah 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 blah, the anomaly is 0. Yeah, right, because it's they pop off ghosts, and I'm assuming some version of that story has been told. So there's a ghost sector which has the opposite amount of central charge, which cancels this off, and it's the stringy version of the Faddeev-Popov procedure that you may be familiar with from field theory. But at the end of the day, yes. These LNs are symmetry generators, and the G's are the fermionic cousin, and so they should annihilate physical states. In the case of L0, we see that annihilation of physical states corresponds to saying, what's the mass of the state? I guess what I've written here is the open. This is the open case. The closed case, right, would have the same thing with also with a sum with the tilde as well. Yeah, and I'll talk about that. I'll talk about how to organize that. There are two different ways of organizing that, and I'll talk about that later on. Let's just list a couple of. Well, let's just look at one important state, which is the 10-dimensional photon that comes from the open string case. So I'm guessing you did that already, but let me just remind you how it is structured. So if I look in the Nova-Schwarz sector, okay, when I have a half there,
So the -1/2 and the 0 aren't modified in the closed string.
no, it's the same. It's the same. It's the same. Sorry, yeah, it's the same. It's the same object. I just have additional copies, so yeah. So let's start with the open. Let's talk about the open string sector for now. And what I'll do is I'll simply go back to the picture I had up here, where I had essentially one copy of that spectrum generating me the open string because of standing waves, or two independent copies giving me the closed string. Okay, and so what I'll do, a quick way of building the closed string sector is to start with just the stuff I got from the open string sector and taking two copies of it with a projection, and that'll give me the closed string sector. So that'll be the quick way I'll do that. Let's talk about the open string. Nova-Schwarz sector. Okay, so there's my ground state. Okay, then so now I want to start working with it. If I started with just the ground state, okay, as you know, so remember this mass shell condition. If you think about it, this is just a number operator. It's saying how many bosonic oscillators have I turned on, how many fermionic oscillators have I turned on with a weight. And so I've turned on no oscillators, right? These don't give me anything. And so my mass shell condition would be telling me that I have a tachyon, okay? And then you already know from, I'm sure, a couple of the classes you've been doing, that state is actually projected out. It's not a physical state in the theory. And so I'm looking now at the next level, which is something that cancels off this half in the Nova-Schwarz sector, okay? And so it can't be something that's exciting with an integer minus, for example, it can't be coming from acting with the alphas, because that would essentially just give me an integer when I count, and that would not give me the next most massive thing, which will turn out to be mass equals 0. Okay, there's something else I can do, which is start with the size, which have half integer moding, and so that'll count as a half for the lowest one, canceling that, giving me a massless state. Okay, and that's the photon.
Sorry, mu equals 0 or 1 don't contribute because I have gauged them away.
Yes.
Okay.
So, well, there are many different ways of thinking about it, but one way is that there are unphysical states in the spectrum that they're non-physical ghosts in the spectrum.
The mu 0 is not physical.
For example, yeah, right, because from the 10-dimensional perspective, if I compute the mod of that state, it would be negative because it's a ghost.
Okay, so for example, like on gauge, I gauge them away.
Mm-hmm.
Okay.
Yeah. So you could always work in like-home gauge, or you could not work in like-home gauge and simply know that when those states show up, they don't show up in any physical sectors. Okay. So one way of seeing I'll say that I meant one way of seeing that is that if I have when I act with higher L's, you'll see additional conditions that come out telling you that. That's a longer story, some version of which you probably did elsewhere. So I apologize for not reviewing it again. Okay. Okay. Let me get back to the story. Actually, before we even act with oscillators, we can act with the zero mode. We can give it some momentum. Okay. So actually, more generally, let me make it an eigenstate of some definite with momentum. I'll just denote as K. U. Okay. So P zero mode turned on, and I'm calling the amount K. Okay. So let me adjust my notation so that I remember that I have some momentum K in general. So the zero is this is standing in for, I haven't turned on any oscillators, but I have some momentum K. Okay. So then I can build some object, as I said, that has m squared 0, that has momentum K, by acting with the simplest of the fermionic modes. Okay. Actually, I can go a little bit further. I can have a superposition of these guys, right, with some coefficient that also is a vector, right? In space-time, you would just call that a polarization. Okay. Right. This is some definite. This is telling me, what direction is the thing. All right, this thing is begging to be called a space-time photon, right? For all the reasons I just said. If you looked at, so Phil, have you done this? No. Yes. Okay. Okay, good. So an exercise, right? Well, right. Okay, so I've done that exercise, right, for you, right? Okay, and m squared is 0, right? How am I doing that? Right, I'm acting with this thing. Okay, I'm remembering. I've got to also have the canonical commutation relations between the psi's. Okay, so let's actually just write those down. So if you want to play with these rather than going to the bar this evening, here we are. So let me write this down, right? And then the technology of this, if you haven't done it before, is no more challenging than the quantum harmonic oscillator, which you've done, I'm sure, in some detail in quantum mechanics class all those years ago. Sorry, I didn't write this down because I assumed that you had done this sort of exercise, so let me just write it down. Yeah, so with that and this, right, so remember, you've all done the quantum, okay. Remind yourself of the quantum harmonic oscillator from whenever you did it in probably an undergraduate class some time ago, right? So go look that up and remember how to build the number operator, right? The bosonic part, just like this, right? And then you created oscillator states, and you've measured how many oscillations were in there by acting with the number operator. Yeah. So you needed this out. You needed the harmonic oscillator algebra, which looked a little bit like this, and you had your number operator. All we're doing here is that we have D copies of the same thing. Okay, it's no harder. So you can actually go through and do these various things. So when I say that n squared on that equals 0, I'm doing that. Or you could just, I can see, I've just counted, and I got a half here. And that cancels the half, the minus the half. Okay. A little bit more interesting, perhaps, is to work at the next level. To go, okay, I've asked that L0 I should have also said positive. I've asked that L0 annihilates this thing. I should also ask that L1 annihilates this thing, and then L2 and L3, right? We'd be here all day. But it turns out that you won't get much more interesting structure beyond L2. Anyway, let me get back on track. Check. So exercise, right? Construct L1, okay, and act on our state that I've constructed here. And ask that be 0. Okay. Commute things around as you might need to a couple of times, and convince yourself that actually what you get from this is a new condition, and the condition is that the polarization vector dotted with the momentum vector is 0, right? Which is precisely what you expect for a photon, right? It's transverse. So yay. Good. So this is a massless vector. In space-time, obeying all the properties we expect from such a thing. Okay, and here's another reason. I forget where the question came from. Here, I think. Maybe it was here. I forget. Right. This is another way we can see that it's d minus 2 because, right, it should be an 8, right, in 10 dimensions, right? It's the 8 v, meaning vector, right, of the SO8 subgroup of SO9, 1, right? The little group of the space-time Lorentz group. Right. There's always a little group which classifies the massless sector. In this case, it's SO8, and this is the 8 vector that is SO8 transformation properties. This massless vector in space-time then. It would not have 8 components if I had all d of these contributing, right? So psi, if you like, psi 0 and psi 1, you can see after a little bit more work, can be chosen as not physical. Okay, so again, I apologize for just sort of stating some of these things without showing them in great detail. But my assigned mission is to tell you about D-branes, not about how to construct superstring theories. So I'm just reminding you of some of the pieces that will need. Okay. So that's great.
Sorry,
What?
where triality it's a way to see the triality of SOA. In that case, in the construction of the states.
Right now, I just have the 8 vector. So until I have a reason to construct 2 other 8s of SOH, I'm not going to necessarily see triality doing anything. But the sentence I was just about to start, when you raised your question, will lead us in that direction. Okay. So here's the sentence. I just did the Noah-Schwartz sector. Why not do the Ramon sector as well? Okay? And so let's see what happens. The Ramon sector, all right, I have now 0 here. So again, I need to look for the massless sector. The massless sector is again going to come from the fermionic stuff, but it's going to come from the periodically moded stuff. Right? And so let's study that for a little while. Okay, I don't need this. So the Ramon sector is very interesting because, as you might remember from having done this just probably yesterday or something, that's where the space-time fermions are going to come from. So let's go ahead and do that. Okay, so the Ramon sector. Oh, sorry. I should have given a name to the projection that gets rid of the tachyon. I apologize. That's the GSO projection. Did you meet the GSO projection? Okay, right. The GSO projection. From some perspectives, the GSO projection is just a means of making sure you have space-time supersymmetry. In a more sophisticated treatment, which you may have done, it's actually also talking about world sheet consistency of the conformal field theory. But from the perspective I'm doing here, it really is going to turn into just a statement about the fact that I have space-time supersymmetry, which is not a priori given. If I have world sheet supersymmetry, that is not a guarantee to have space-time supersymmetry. So I need to actually ensure that. So the GSO projection, I should have made explicit here, removes the tachyon. Right, the tachyon, if you recall, I would have made by just looking at this vacuum and asking what its mass squared is. Mass squared is minus 1 over 2 alpha prime, right? Coming from no oscillators excited, 1 over alpha prime minus 1/2, right? And the GSO projection in my conventions is going to be that I project onto minus 1 to the f equals minus 1. What I mean by that, sorry, no, plus 1. I basically count the number of fermions in my state and assign that to be even. That's the GSO projection. In this convention, then, the vacuum actually has fermion number minus 1. Okay. So I just need to say that because I need to make the equivalent choice on when I come to the Ramon sector as well. And so otherwise I I don't know space-time supersymmetry. So, okay. Let me proceed to construct the Riemann sector. So one of the things that you can notice is if I just look at the 0 sector here, I put 0 and 0 there, okay, or on the other side, okay, I just get that a family of things anti-commute to give me eta mu nu, right? And you recognize that as a Clifford algebra. This is not me. Right, and so that if you like, is the first sign that secretly these guys are telling us how to build space-time fermionic states. Okay, and so one of the things I want to do is organize things with respect to that, so that I can really keep track of the fermionic content. So naively then I have right. So the Clifford algebra. That's what that 1/√2 is for, just to give the standard Clifford algebra normalization. Okay, so what I want to do is construct just trying to see a quick way of saying this so I don't spend too much time on this. Okay, well, we should do it. Right, space-time Lorentz. Since we're worried about space-time Lorentz properties, particularly the fermionic content, it's actually useful to build the space-time Lorentz generators explicitly. And you've probably seen this. You've probably seen this elsewhere. This isn't a string theory thing. This is just a thing. But I can actually build the space-time Lorentz generators this way. Okay. And so these 0 modes of the fermionic sector, because they form a Clifford algebra, they also can keep track of the space-time Lorentz generators that then satisfy, they're antisymmetric, and they satisfy the space-time Lorentz algebra as generators, which, okay. Right, stuff involving etas and j's. Let me not write it out. We're not really good at etas. Okay, this is schematic. So we put it in. Okay. Let me explicitly construct then an object that keeps track of the the space-time Lorentz properties. Let me give it a different name to distinguish it from this general algebra stuff to the stuff we're doing in string theory. So I'm going to bring out that factor of 2. Okay, I'm going to build it out of these guys as follows. So this object counts Lorentz properties or states on the world sheet. Okay, and there's a nice basis that we can build things explicitly from, which I've forgotten to write down the name of it. That will allow us to do a very, very straightforward counting of everything without worrying too much about being in some sophisticated language. It's a definite basis in which I can build measure the Lorentz properties. And so this is something that you'll do a lot when you're thinking in higher dimensions. When you're thinking, right, well, what are we really doing? We're worrying, for example, about rotations in the full 10 dimensions, or really in 8, the 8 transverse dimensions. Another way of thinking about 2 of them not contributing is that, if you like, there's always a gauge in which I can align the string world sheet in the 0 and 1 directions, and then everything else is transverse, 8 transverse dimensions. That's maybe a nice way of organizing your thoughts, in addition to my other answers about those 0 and 1 sectors. So I want to think about rotations and Lorentz transformations in that whole remaining 8 dimensions. And one way that you'll come across people think about higher dimensions and rotations and Lorentz transformations is by breaking everything up into 2 planes. Because none of us really think in higher dimensions, right? We like to think that the general public admires us for being able to do that, but really we don't. What we do is we cheat, and we just do pretty much everything we do is just 2-dimensional pictures dressed up, right? One of the ways of doing this is so what have I done here? If you look, I put I equals 1, I get 4 and 5, and you know, I equals 2, right, etc., etc. So I build things up in pairs, okay? And then basically I just look to see what's going on in each of those pairs. And I also let me, although we'll throw it away. Let me also look at this convention choice where that's 0, 1. Let me also write that down, okay? And then the way I've written it in this language, these guys are creators, and these are and the minus guys are annihilators. Again, this is more than I need to teach you basic stuff about D-branes. But I find it's a useful language for even when you start doing things more exotic with D-branes, you start intersecting them and wrapping them around things and what have you. Still, organizing how all of that works with this language is extremely useful. So I'm trying to bring out maybe a little bit more than I need in order to help you for later calculations. Okay, so what am I doing with all of this, right? Annihilators, creators on what? Okay, so now I go back and I say, this is the basis I'm going to use to discuss my Riemann sector states, which I've erased. Right. Well, it's 0, right? It's always going to be 0. The point is that I have a whole degenerate set of 0 states, 0 mass states, yeah? But they travel together in an interesting way, and they build the components of what we'll see as space-time fermions. Right now, there are too many of them. Right? There's actually 32 of them. 2 to the 10 over 2, because that's how many components we have. Okay. Right. So actually, let me list that down. So the basis I'll use then is that I'll have an eigen states of these things are either plus or minus a half. Okay, which I'll call S. Okay, and I'll call them Si, where the I is either 0, 1, 2, 3, or 4. Right, so I'll have S0, and I'm going to call S1, S2, S3, S4. Right. So these guys are essentially up to a normalization, the eigenstates of this operator that's counting Lorentz, space-time Lorentz properties. Okay. Right now, talking about the the spin, which is what we're interested in. Okay. So this is either plus or minus a half, plus or minus a half, plus or minus a half, plus or minus a half. There's my 32 different possibilities. Yeah. Okay. So so 2 to the 32, 2 to the 10 over 2 equals 32 states. Okay, when you go through, S0, there's a factor of I. It's a factor of I in how these S's are eigenstates if you're keeping track of the factors. Okay, so if you go through, you check this 32 actually breaks up into 2 copies of a 16. The point being that if I there's a even number. Let's see, what's my convention? There's an even. Yeah, an even number of S's change signs. So I have 32 massless states that I make with those psi zeros. 16 of them like to be with each other, and a different 16 like to be with each other. So that's what justifies this. Okay, and then so now I get to do the physical state condition. So now physical state condition, I get something non-trivial from G0. Okay, and if you work it through, so unfortunately I've erased G0. Go back in your notes and look at G0, and you see the leading piece, the piece that is going to give me anything non-trivial, is going to have a psi 0 in it. Okay, and if you look, you'll see that that's alpha 0, alpha 0, psi 0, mu. Sorry, alpha 0 dotted with psi 0, right? But remember, that's 2 alpha primed to the half p mu, if I remember what alpha 0 is. Let me unpack the dot, right, so that I'm explicit. This is then psi 0 mu. Right, so that's what this is. And if you think about this, this is a momentum space version of the Dirac equation. Yeah, right. Yeah, this would be this would be d mu in position space, right? And that's the thing that makes it slash, right? Because it's again a matrix. Yeah. So this is the Dirac equation. And there's no mass because there's no mass, because it's the massless Fermi. So we've seen the analog, the fermionic analog of this story over here, where we saw, right, what we have, right, Maxwell's equations, right? But Maxwell's equations essentially say I have this A and it's transverse. Right, that's the content of Maxwell's equations. And then we're having the Dirac equation over here in the fermionic sector. So that's rather nice. Okay. We still have rather too many states compared to what I was looking for. But there's an additional Yikes, I'm missing a page of my notes. That's very annoying. Okay. Okay. So, hi. I think I'm going to say this right from memory, and I apologize. I think that should translate into setting S0 into plus or minus a half, and I think in my conventions it's actually a half. Which, if you think about it, is analogous also to the physical state condition making a choice about the sector. And so what that does, almost finally then, is that I have an 8 and an 8, right? Because I basically have, S0 can do whatever it wants, all the other guys can do what it wants, but now in each case I now fix S0, so I lose 2 choices, right? I divide my number of choices by 2, that's a better way of saying it. Okay, so this becomes now 8 possibilities and another 8 possibilities. Okay, so I'm going to label the final choice coming now from the GSO projection. The GSO projection then says I pick one of these, right? It either so in the conventions I'm using, which is not on this page, which is on the page that's missing from my notes, projects onto even number of pluses. Okay, and so that either, depending upon how I set things up, it's either this guy or this guy. And the point is that either choice is equivalent. Okay, and so I have one choice which I can call the 8S, and then there's the equivalent choice which is called the 8C, the sort of conjugate one to that, the one that's built out of the it's either that one or that one, depending upon how I had decomposed those S's. So the point is that right now these are equivalent choices, and if I only have one copy of this fermionic 8 floating around in space-time, it doesn't matter whether I call it the 8S or the 8C. They're completely equivalent. Only in a situation where I have both of them will I distinguish between them. Okay, and for the open string, it's one or the other. When I come to the closed string, and I have 2 copies, one from the left moving sector, one from the right moving sector, then I have to say, is one the 8S and the other the 8C, or are they both of the same type? And that's what gives me type 2A versus type 2B. Right? You probably had this discussion before. Is that how you discuss the difference between type 2A and type 2B? And did you? I was told you had a course on superstrings. Is that not true? No, really? I want to know. Did you?
Yes.
Okay. And so did you hear about this stuff?
Yeah, sure.
Okay, good.
I was just curious why the choice of S and C for the notation.
One is spinner and one is just conjugate. I think that's the historical reason for this. Yeah, it's nothing sophisticated, as far as I know. And you can see there's nothing special about one versus the other. Right? It's just does one have an even number of plus signs or the other have an odd number of plus signs? It's not really anything. Yeah, and that came down to a choice of conventions here about what's plus and what's minus. Put differently, in the different pairs of coordinates that give me the 2 planes, am I going around that way or am I going around that way? And then when I build up the content of a spinner, how I make it up out of all of those different SO2 spins. And it's just convention as to whether it's made up of one set or the other. So at the end of the day, I have 8 components of this massless thing. It satisfies the Dirac equation. Life is good. It's the super partner because of the GSO projection. It's now I just have the right amount of content to be the super partner of the photon. So now I have an n equals 1 10-dimensional vector multiplet in the open string, massless open string sector. Okay, which is presumably familiar, and I have 2 minutes, so I'm gonna use those 2 minutes now just to remind you about the closed string. Or not. I have 5 minutes? Oh, that's very good. Let me, 1 second. There was something else I was going to mention. I didn't want to forget it. No, it's good. Oh, and that's how you get the standard model. No, just kidding.
So the states for the 8 representation acts are S0 equals 1/2, and the others are 3.
No, S0 is a half from the physical state condition, and that's now fixed. I've made that choice. Okay, and so if you like, now I have 2 to the 8 over 2 things left over.
Okay.
Yeah. Yeah, and then I can divide those into, does it have an even number of plus signs or an odd number of plus signs, if you want to count that way. Yeah. Okay, so closed string sector. So as I said, the closed string sector I can think about as from the point of view of exciting things with oscillators, okay, on which oscillators are excited or not. I can think of the closed string sector as simply just like the open string sector, except I have 2 copies, one going for the left, one going for the right. Okay, and I just need to remember that factor of 2 when I worry about the zero modes to get the momentum right. But other than that, I'm done. Okay, so in that way, I can easily make the closed string sector, the massless closed string sector. That's all we've done so far, by just tensoring together what I've seen here. So this is where you get the language that you'll see a lot in the literature, right? So tensor together 2 copies. So 1 for left, 1 for right. Of this to build close. Okay, so let's just do it. Okay, and basically this becomes an exercise into how many ways can I write 8 times 8, really, in simple terms. So basically I have the 8 vector, okay, and I have the 8. I don't know, let's spinner, okay? Okay, and now I multiply this by 8 vector. Okay, now I have a choice, right? So for the left moving sector, let's say I have 8s. So I can either also do that, or as I said, now I have both. I can make the choice as to whether I have keep them the same or not. Okay, so that's why you have 2 10-dimensional superstring theories. So 8 times 8 is 64. Okay, and the 2 important ways I'm going to write 64, I'm either going to write it as 8 plus 56, or I'm going to write it as 1 plus 35 plus 28. Okay? And that's about as hard a calculation as I'm going to do today. Okay? Right, the second comes from the common Nova-Schwarz sector, right? And so this is why it's called the Nevers-Schwarz sector, due to a spectacular failure of imagination in naming things. So basically, 8 vector times 8 vector gives me 1 plus 28 plus 35. And you know these people very well. Okay. Anyone care to call out what they are? Okay, the dilettante.
Anti-symmetry field and radical field.
Great, yeah. So phi, b mu nu, and g mu nu. Okay. The same thing is going to be present for this as well. Yeah. And that's good because, you know, unless you're doing something really extra nuanced, a closed string ought to have a graviton. It ought to have the thing under which it's Nevers-Schwarz charged, which is the B mu field, which you could also think about, as we will, as the thing that measures how much it can wind, and the dilettante. Okay, and then finally, and then I should probably stop in 1 minute. Then I also have from the Ramond sector. So this is Nevers-Schwarz, Ramond, Nevers-Schwarz, Ramond. So from the Nevers-Schwarz sector, I have that. I have Ramond sector. Ramond sector can either be 8s times 8s or 8s times 8c. Okay, these are going to be two different things, and as I said, those will give me the different theories. So let me write that out. So type 2, this is type 2a, and this is type 2b. And I guess I should have said the string, open string stuff that we found is the type 1 string. Kind of, it's not quite finished. This is the 8 plus 56, 8 vector plus 56. Tensor is called, and then up here I have a 1 plus 28 plus 35 again. And these I'm going to call space-time fields. I'm going to call them C. This is a vector, so it has an index mu. This is a 3-index creature, if you count it up. This is a scalar. This is an antisymmetric tensor again. And this is also something that has 35 components, but it has 4 indices, which should confuse you, because if you count, you get 70 components. But there's a self-duality condition on this in 10 dimensions that I'll remind you of later on. So I'll put a little thing there to tell you that I picked a self-dual sector, which reduces that number of components down. And so that's all I'm going to say for this first lecture then. I have the type 2A spectrum, the type 2B spectrum, the type 1 spectrum, which is just this. Take your pick, SOC, and that's it, right? This is an n equals 1, Super-Yang-Mills multiplet. Okay, this is instead n equals 2a or n equals 2b supergravity multiplet. And the supersymmetry is completed by having these antisymmetric tensor fields. Okay, so I'll stop there.
Thank you. Is there a couple of questions?
Yes, Clifford.
Why don't you have like 8
Right, because it doesn't matter. Basically, S only exists to tell me it's different from C. But if I have only S, I could call it C instead. In other words, this is also 8C cross 8C. It's the same thing. I know it sounds really confusing. It's just I have this 8 thing, and there's a different. Yeah. I don't know. It's just sort of. It's only meaningful to use the label to distinguish it from the other one. So when it's on its own, it can be either. The other question, which I'm going to ask, I just ran out of time, so I'll pick it up next time, is, of course, so this is a boson, this is a fermion, this is the supermultiplet, and I've just shown you the bosonic part of the type 2 supermultiplets here. I also have the Neveu-Schwarz times Ramond, or the Ramond-Neveu-Schwarz sectors, and those will give me space-time fermions, which are the superpartners of these guys. Again, it'll turn out that it's basically 8 times 8 equals 64. I'll just write 8 plus 56, or 1 plus 28 plus 35 in a fermionic way. Again, so I'll pick up with that afterwards.
Just the notation and the lower index of this 56 is.
Oh, it's just it's all again it's old-fashioned 10-dimensional spinor notation. It's not spinor notation. Group theory. It's some tensor representation that is 56-dimensional of SO8. Yeah. It's to distinguish it from. Okay, let me just tell you. There's an 8s or 8c in the fermionic sector as well when I do the multiplication for the Neveu-Schwarz Ramond sector. Okay, but there's also a 56, and that'll be, turns out, come in 2 varieties as well. I've lost where you are. Well, I'm telling that to all of you anyway. And that's fermionic. So the T on there is to tell, this is some tensor representation. These are fermionic guys. What are these guys? This is a if you like, this is a dilatino, and this is a gravitino. This is something which in space-time would have a space-time index and a fermionic index. It's a superpartner of the gravitino. Really correctly, the two of them go together to give you superpartners of the whole gravidilaton multiplet.
Okay, let's thank you again, please.